Hello everyone, welcome to the next lesson of numerical methods. In the last lesson we have learned about the details of value decomposition, how those value decomposition techniques can be used to find out the solutions of simultaneous linear algebraic equations. So in this lesson we will go through some of the more detailed properties of value decomposition. So let's get back to the slides. There are two different LU decomposition techniques, the Doolittle-LU decomposition and the Crouch-LU decomposition. The Doolittle-LU decomposition is the same procedure that we had followed in our previous lesson, lesson 22. In that lesson, we had converted our original coefficient matrix into a lower triangular matrix and an upper triangular matrix. And there were some certain properties of those two matrices. In the lower triangular matrix, the principal diagonal elements were 1 and the upper elements above the principal diagonal were 0. So this was the specific type of lower triangular matrix that we determined in the last lesson. And in the upper triangular matrix, only the lower elements below the principal diagonal were 0. So that's the main LU decomposition technique that we used in the previous lesson. So it's also named as Doolittle decomposition method. It was determined in this manner. But there is another type of LU decomposition technique which is known as Crouch LU decomposition. But in this case, the shape of the two different matrices, the lower triangular and upper triangular matrices, have some slight difference. For example, in this case, the Crouch-LU decomposition, the principal diagonal elements are not 1. Rather, in the upper triangular matrix, the principal diagonal elements are 1. So in both of these cases, we see if we multiply these two matrices, the lower triangular and the upper triangular, we will get the original A matrix. So the difference is in the principal diagonal. Okay, so I hope you were clear about the differences between the Doolittle and the Crouch-LU decomposition. The Crouch-LU decomposition method is very much suitable for computational applications. So Crouch-LU decomposition has higher preference than the Doolittle decomposition. If you want to implement the LU decomposition in MATLAB course or Python course. So how these Crouch-LU decomposition techniques are implemented? The Crouch decomposition approach generates the upper triangular matrix and the lower triangular matrix by sweeping through the matrix rows and columns. For example, we sweep through the first column in this way of the whole coefficient matrix and we get these values. Similarly, then we go through the first row and then use this formula to get these values. So using these values we can get the lower triangular elements, and with this formula we can determine the upper triangular elements for the first row and first column. After we have swept through the first row and the first column, we go through the second column and second row in this way. Okay. Now remember, we do not consider the whole second column because this term is being considered in the first step. So we have just swept through the first column and then the first row. In the second step, we go through this column and this row. So with this we use these formulas. Okay, we use these formulas to determine the lower triangular elements and the upper triangular elements. After we have gone through the second column and the second row, we go to the third column and third row and so on. We can easily determine these values, these lower triangular elements and upper triangular elements with these formulas. So we are not going through the details of finding out how these formulas were developed. We are not showing you the proof. These formulas can be straightforwardly used in your MATLAB code to implement the Crouch-LU decomposition. Look at this, the I terms I equal to 1, 2, 3, n. These I terms denote the rows. I is for rows and j is for columns. So for example, in the first column we sweep through from row 1, row 2, row 3 to row n, and then we sweep through the columns. Since the first element of the first column has already been covered, so we go from j equal to 2, 3, 4 up to n. We do not consider the j equal to 1 term because that has already been considered in the case of I equal to 1. So there's in this way we can determine how the row elements and the column elements of lower triangular and upper triangular matrices can be calculated. So then in the same case goes for these. In the second scenario we go from j equal to 2 to n minus 1, and I equal to in the same manner that we used for this purpose. So in this way we can use these formulas to implement the Krauss-LU decomposition method. So you see there is another equation that is described here, which is LNN terms. That means this equation is being used for the diagonal elements. LNN equal to ANN minus this term. So this is the one used for determining the diagonal elements. That means this is the diagonal element of the last row and last column. That means this one. So this equation is being used for this last element. Okay, this last diagonal element. The Krauss-LU decomposition method has several benefits. The first one is that you do not need to save the intermediate values into the storage space of your computer. So for example, if you remember the upper triangular matrix, the elements of the upper triangular matrices can be stored in the 0 elements of the lower triangular matrix. So that's the benefit of Krauss-LU decomposition method. So we can easily dynamically calculate all of the lower triangular matrix element and the upper triangular matrix element and replace those values in the original matrix. That means a single matrix is enough for storing both the lower triangular matrix and the upper triangular matrix, and we can easily store them in the original matrix A, because we are sweeping through rows and columns. So once we determine each row and each column, then the original values of those rows and columns are no longer necessary to calculate the subsequent elements. And that's why if you are given a original matrix or original coefficient of matrix A, then you can easily dynamically determine the lower triangular and upper triangular matrices and substitute those values in the original matrix elements, because those row elements and column elements are no longer necessary. So that's why this Krauss-LU decomposition method is very much computationally efficient, because you do not need extra storage spaces. So in this lesson we have learned about the Krauss decomposition, LU decomposition method. The Doolittle decomposition method was covered in the previous lesson, and we have seen that the Krauss-LU decomposition is very much suitable for the computational applications. So please try out the MATLAB code that I have attached with this lesson to implement the Krauss-LU decomposition. It's a very straightforward computational implementation. You just write down the formula in the MATLAB code and then try the code in the loop. So please go through the details of the code to understand how those formulas are being used to find out the solutions. So in the next lesson we are going to find out another extension of LU decomposition method, which is also known as the Thomas algorithm. So this Thomas algorithm was specially designed for tri-diagonal system, and we will see the details of this algorithm and how this method can be used. So till then, thank you so much.